Hello, I'm Savannah Scott, and this is my presentation on finding a target by using reinforcement learning. So the outline for this presentation is going to be, first we'll look at the motivation, then we'll talk about the problem formulation, then the mathematical background, the simulation, and then finally the conclusion. So the motivation behind my project is that there's been a large increase in using UAVs for search and rescue missions. This is because UAVs have low manufacturing costs, they're easy to deploy, and they're highly flexible and can be used in a wide variety of situations. UAV search and rescue has predominantly been human operated, so think of a pilot inputting a path for the UAV to search, and the pilot is watching the camera while the UAV is searching, and they're looking for the target on the camera. And while this has worked, there are certain conditions that kind of make this unsuitable. The pilot might not be able to always have good communication with the UAV. If they're searching in a mountainous area, there might be areas where the UAV and the pilot can't communicate with each other. And so the goal of this project is to kind of look at how well reinforcement learning works in order to train an agent to search an area and find a target, to see if this could potentially be applied to UAV search and rescue. So before I get too deep into the problem formulation, I wanted to talk about a few important definitions. The first one being the state. This is the current position of the agent within its environment. Then there's the action, which is the action that's taken by an agent when it's in a certain state. The reward is a point value that the agent receives for doing an action. The Q value determines how good an action was at a particular state. Epsilon greedy exploration means that the agent is going to select an action with the probability of epsilon, or it's going to select the action with the greatest reward with a probability of 1 minus epsilon. And greedy exploration means that the agent will select an action with the greatest reward every time. So I looked at two different reinforcement learning algorithms during this project. The first one is Q-learning. This is an off-policy algorithm, which means that the next action is selected in order to maximize the Q value function, and it does that instead of following the current policy. In this algorithm, the actor learns from its actions, and its behavior policy is epsilon greedy, so that's how it chooses its next action, and the update policy is greedy, so that's how it chooses its next Q value. The other algorithm that I looked at is state action reward state action, or SARSA. This is an on-policy algorithm, which means that the target policy is the same as the behavior policy. It learns the Q value based on the action performed by the current policy, and this algorithm trains the critic to estimate the return of the future rewards. Both the behavior policy and the update policy are epsilon greedy. When looking at the pseudocode for the two algorithms, they are relatively the same. The biggest difference between the two of them, again, is just how is that Q value function updated. So with Q-learning, it's looking for that maximum value in order to maximize its Q value, and SARSA is looking at that is following the epsilon greedy policy to find its next Q value. Both of the algorithms choose their next action using the epsilon greedy policy, but they choose it in a different position within the pseudocode. So in Q-learning, the next action is chosen within the main loop, and SARSA, the next action is chosen outside of the loop. And this kind of gives SARSA the tendency to stay away from the obstacles a little bit more than Q-learning. And that'll be shown in the next couple of slides. So I don't want to get too deep into the mathematical background, but the goal for the agent is to maximize the reward, and this is represented by that first equation there, which is known as the expected discount return function. The discount factor is included in order to force the agent to kind of focus on the immediate reward rather than focusing on the future reward. The state value function describes the goodness of the state by following the policy pi, and the action value function determines how good an action taken by the agent was. Since the goal is to find the optimal solution, the optimal state and action value functions are used and they are going to return the highest reward for both of the functions. The optimal action value function actually satisfies Bellman's principle of optimality, and that's that equation on the bottom, and that equation is saying that at any time, for any state action pair, the expected reward from the starting state taking a certain action following the optimal policy is going to be equal to the expected reward. So it's just what is the reward that you're expecting for following a certain state action pair. This is just kind of showing that expansion of the Bellman policy for both Q-learning and SARSA. Again, the biggest difference between the two of them is that Q-Learning is following that greedy target policy, and SARSA is following that epsilon greedy policy when updating their Q values. And this is just another way to reiterate that. Moving on to my simulation, I created this 10 by 10 grid world in MATLAB. The red dot represents the agent, the blue square represents the goal, and the black squares represent obstacles. I used the MATLAB Reinforcement Learning Toolbox in order to run the simulation and to train the agent. The rewards that the agent received were 20 points for getting to the target, -2 points for hitting an obstacle, and -1 point for moving. And the reason why I have to give the agent -1 point for moving is because it's trying to maximize its rewards. So if it had a positive reward for moving, it's going to try to fill up all of the gaps before it gets to the target because it's getting a positive reward every time it moves. So that's kind of why you have to give it a little bit of a deduction for moving, but you don't want it to be too much because then it might just stay at one place. Each episode could run for up to 200 iterations, which means that the agent could move up to 200 times before the episode ended, or the episode would end once the agent found the target. So these are the results from using the MATLAB toolbox for reinforcement learning. The light blue lines are the episode rewards, and the dark blue line is the average episode reward. So notice at the beginning, the episode reward jumps around a whole lot. It's kind of very sporadic. And like I mentioned earlier, the agent was able to move 200 steps before it terminated the episode. And you want it to move a lot in the beginning because that's how it's really going to learn that, oh, hey, the more that I move, the more points that I get taken away from me. So maybe I should move a little bit less. And you give a very high reward value to the finding the target because then the agent starts realizing, oh, the less I move, and every time I find the target, my reward gets higher. So at the beginning, it starts out by moving several spaces and hardly finding the target. And then kind of towards the middle, it starts to always find the target, but it's still moving a lot. And then at the end, when it converges, that means that it's realized, okay, this is the shortest path that I can take to the target. This is going to maximize my reward. And the Q-Learning agent converged around 188 episodes in, and it converged to a final value of 4, which was the maximum reward that the agent could receive in this environment. And this is the path that it planned. Notice here how the agent, it's not hitting the obstacles per se, but it's more kind of hugging up against them more than the SARSA agent will, and I'll show you that slide in a minute. And that's what I was kind of talking about within the pseudocode, how where you choose your action kind of determines how close you might get to the obstacles. So SARSA, relatively the same. The biggest difference here is that it did not converge until 197 episodes in. And this is the path that it found. So again, this one's not necessarily as close to the agents, as close to the obstacles as the Q-Learning agent was. One thing that I discovered this weekend when I was working on my report is that SARSA typically converges a bit faster than Q-Learning. So I created this larger 20 by 20 grid world. I had to kind of change around the reward system for this one, as well as make the target a little bit bigger. So now when it reaches the target, it's going to get 200 points. When it hits an obstacle, it's going to get -20 points, and it still only gets -1 point for moving. I also made that target bigger, but each of those squares within the target is a termination condition, and I just kind of included this in order to help reach the target a little bit faster and converge quicker, because this grid world took a lot longer to run for me. So when I ran everything, these were the results from that. One thing that I want to note here is that now SARSA is getting closer to the obstacles and kind of hugging around them a bit more than Q-Learning did. Another thing that I want to mention here is that SARSA's reward was 166 and Q-Learning's reward was 167. Q-Learning was able to get the maximum reward value, but SARSA got one under it. And that's because it moves up that extra step and then over to the right to get to the terminal state instead of just going directly to the right to gain that extra point. And I actually ran the SARSA training algorithm a couple times to see if it would improve, and it never did. It always stayed at 166. This was always the path that it came with. So honestly, this just kind of ended up leading to a few more questions. But I did answer the question of, does SARSA converge faster? It did in this world. So This one, SARSA converged in 610 episodes in this world, and Q-learning converged in 616. Q-learning also took about 40 seconds longer to converge than SARSA did. My conclusions from all this is that, first of all, both of the algorithms were very easy to use and I was able to understand them well, and I think they work really great for single agent explorations. I learned that different map sizes are going to lead to different convergence times, not in the sense of, oh, a bigger map is going to take longer to converge, but more in the sense of, oh, this map might be better for SARSA than Q-learning, or that map might be better for Q-learning than SARSA. I really thought that I would determine if one was better than the other, especially when I ran the 20 by 20 grid world. But it kind of just made my results a bit more inconclusive than I would have liked. My plan is to hopefully have some time to look into why SARSA didn't try and go for that extra point, why it didn't converge faster than Q-learning in the 10 by 10 grid world, and just hopefully try and answer those questions for my report. We will see. Potential future works. I read a couple of papers that made the grid world kind of more like a maze. So it was like the agent trying to get through the maze to get to the reward. And I just thought that was a really interesting way to train the agent and see how it works. Also, like I emailed you about earlier, my initial project proposal was multi-agent reinforcement learning. And I just unfortunately did not have the time to get it up and running the way that I wanted it to, and I wanted to be able to have results to present for the presentation and write about in my report, which is why I had to go back down to single. But I think in the future it would be very interesting to start looking at multi-agent reinforcement learning to search the whole grid world. Thank you so much.